Hello. Welcome to another lecture on speech signal processing. So, if you recall, last class we were talking about a binary pattern classification problem, males versus females, or enemy target is present or enemy target is not present, or in banking, whether it is indeed the customer or it's an imposter, right? So, there are only two classes that we talked about, and the way we did is we talked about finding a density function which describes the one of the only two classes, right? Present or not present, customer or not customer, male or not male. We are assuming there are only two classes, male and female. So therefore we try to fit a density function having a lot of data. So we had data about the males and built a density function. We had data from females and built a density function, and given an unknown, we don't know, right? When you are doing an actual pattern classification problem, we were looking at a measurement that we obtained where we did not know whether it was a male or female, and we had to make a decision, right? And the way we made a decision is based on the idea that which one is more likely to have generated that particular observation. So we talked about if I have the male distribution and the female distribution, given a measurement x hat, which one is most likely to have generated that particular measurement, right? So if this is larger, right, then we say it was a male. If the female was larger, so this is in this direction, we said that it was a female, right? Obviously, we are going to make some errors, right? And we talked about this, the probability of miss and probability of false alarm when you're talking about in terms of the defense kind of an applications, or sometimes it's called type 1 error and type 2 error in economics and so on. So the names are different, but the idea is very similar, that once I decide that I have a threshold, and above that threshold I'm going to classify this guy as male, then there are some females who are going to have heights that are greater than the threshold. So if I say 5 feet 5 inches is my threshold, above 5 feet 5 inches I decide it's a male, there are some women who are above 5 feet 5. So I am going to make errors in classification, and that error is this guy. And similarly, below 5 feet 5 inches, I am going to always classify that as female, but there are going to be some males who are going to be having heights below 5 feet 5 inches. So there is also going to be another type of error, right? So this is present versus not present. So the false alarm versus miss, or misclassifying females as males and misclassifying males as females. These are the types of errors that you are going to get, right? So, and the idea was, if I move the threshold, or a customer is actually the correct customer or it's an imposter, if I move it, I will reduce one of the error, but the other error will become larger, right? So I might reduce the false alarm, but then the probability of miss becomes very large, right? And there's a cost associated, right? If I miss an enemy target, they are going to put bomb. Or if I push it the other side, I'm going to have lots of false alarm. So I'm always going to be saying there's an enemy target when actually there's nothing. So keep shooting missiles, and that is also harmful, right? Because I'm losing money just shooting it into the air and burning it up, right? So this is where we talked about where there's only one measurement, one variable that I was talking about, right? So based on the height, I was trying to classify whether it's a male or a female. I can probably increase my, measurement accuracy, right, or my decision making by having more measurements. Maybe that will help me decide better whether it's a male or a female. So one way that I can think of is measure both the height and the weight, right? So then I now have two measurements. So there's a height measurement that I have, and there is a weight measurement that I have, right? Both of these are equally, useful for determining, because generally males are, taller and women are shorter. Therefore, I can use that as one indication of the gender, whether it's male or female. Conversely, I can also look only at weights, right? And then if I look at weight as a variable, right? So I measure weights from a large number of population, then I can fit up this Gaussian. Again, they'll tend to be almost a normal distribution, right? Because that's again independent measurement. So we can have weights, two PDFs, and determine that if the weight is above 55 kgs, I will classify them as male. Less than 55 kgs, I'll class them as women. Again, there are going to be errors. Why? because there are going to be some men who are less than 55 kgs and some women who may be more than 55 kgs. So, like one variable measurement of height, one variable measurement of weights also could be harmful, I mean, or could not be as accurate. Okay. So, then we can say, why not take both height and weight and then determine a distribution and then classify whether it belongs to the male class or female class. Now, I have two measurements, and with these two measurements, maybe my decision making can become better, right? So, if my height is 6 feet 2 inches and my weight is 70 kgs, maybe there's a higher, more higher probability of being correct that it's a male and less correct, probability that it's women, right? So, therefore, I can increase some useful measurements which all will help my decision making better. Okay. So, that is the basic idea of having multiple measurements. So, let me talk about the multivariate Gaussian. So, you might have two measurements or three measurements and so on. So, now my measurement becomes a feature vector with multiple measurements, height, weight, something else, right? So, with this kind of height, weight or chest size or something, I don't know, we can have multiple measurements, and based on that I can be classifying it as a male or a female. And first, to start with, of course, I need supervised data. I need height, weight and chest measurement of all males, height, weight, chest measurements of women, and with these two I find out, with these three measurements I build a three-dimensional Gaussian. So, there it is a single Gaussian. I can have a two-dimensional Gaussian, which is called a bivariate Gaussian. For example, in the case of this two-dimensional data, I can build a two-dimensional Gaussian, right, with height and weight as the two parameters, or I can have a multi-dimensional like height, weight, chest size, and I can have three measurements, and I can again build a Gaussian for that. We will see what that is called a multivariate Gaussian, right, and we will talk about something called the mean vector. Now, it will not be variance, it will be called covariance. We have to look at the relationship between these these measurements. And the idea is that if I have three variable, three measurement kind of thing, I do it for men and I do it for women, and then I am standing outside. So, somebody now shouts, the height is 6 feet 1 inch, the weight is 70 kgs, the chest measurement is 32 inches. Now, can you tell me whether it's a male or a female? Now, with these two density functions with a trivariate Gaussian, right, I now look at the likelihood of this 70 kgs, 6 feet 2 inches, 32 inch measure waist height measure, chest measurement. Can I decide whether it's a male or a female, which is more likely to have generated? Now, I have to look at it, but now it's not a single variable, I am looking at multiple variables, right? That is why it is a multivariate Gaussian, right? So, in a multivariate Gaussian, depending on the number of measurements, the measurement vector is now, it is going to be in terms of vectors now of measurement, right. So, it will be let us say three-dimensional vector, right. Therefore, the mean will be, remember the sample mean is just nothing but the, so let me just see here. So, let us take the case of a bivariate, okay. So, now we will have two measurements, right. So, let us say that the two measurements are heights and weights, okay. So, if I independently look at, let us say the first measurement is height x1 and the next measurement is weight x2. So, if I do it, I will plot the x1 height for the male and the x2 height for female. Similarly, I will plot the for weight and x2 measurement for weights and a female weight measurement, or I can have jointly looking at this, and then this x1 becomes the one measurement, x2 becomes another measurement. For the male itself, I am going to look at it. Now, it is like a three-dimensional plot. For males, I look at x1, for males, I look at x2, and I find out the number of people with a height of some x1 measurement and x2 measurement being so much, x1 measurement being so much, x2 measurement. So, I will get a three-dimensional plot, right. In two-dimensional, x-axis was a variable and y-axis was how many of them were having this. Now, x1 and x2 are going to be the x and y axis, and how many of them we are going to fit a a curve, a bivariate curve to it, where the outside the page it comes out and shows how many of them have these measurement kind of thing, and you are fitting a closed form equation for it, and that closed form equation is this bivariate or multivariate that we are going to deal with. Okay. So, if you are looking at bivariate, there are going to be two, in the case of a single variable, there was a mean value and a variance value that you have to measure. Now, in a bivariate, now if I have two variables, then the mean itself will have the two means, the mean of the weights and the mean of the heights, right. So, those two itself will become a two-dimensional vector for means. Now, we have to worry about what is the relationship between the variables themselves. So, heights by itself will have a variability, right, that is a variance of height which we understand. The weight itself will have its own variance, which you know is a variability of the weight itself, but there is a relationship between the height and the weight also that has to be captured. That is basically where we are talking about the covariance, the relationship between the height and the weight. Why are they related? They can be related. If it's 0, that means they are uncorrelated, they are not related to each other. But you should expect that there is some relationship. Why am I saying this? So, if you look at heights and weights, right, typically if somebody is taller, they tend to be heavier, right. I mean, their bone mass is higher, right. So, typically you see most people who are, you have somebody at 4 feet 5 inches, the weight being 80 kgs, that is very rare. They are really obese persons, right. But typically when people are shorter, they tend to be also less heavy, right. So, similarly when somebody is 6 feet 8 inches, typically they will be having a larger weight, there will be some 80 kgs, 90 kgs, right. So, if you look at this height, right, and this weight, typically when the height is larger, you will see that the weight also becomes larger. So, you can see this if you look at the population, right, you will generally see that there is a some kind of increase in height means an increase in height weight. So, you will see that there is a some kind of a y equals x kind of a curve that is happening, right. So, as x increases, y also will start increasing, right, that when the height starts increasing, the weight also starts increasing. So, the height and the weight are correlated variables. That the height indirectly tells you some information about the weight, right. So, when the height increases, you expect the weight also to be slightly higher, okay, and that is what is showing here. So, if you look at red, those are all women, and if you look at blue, they are men, right. Generally, men are taller than women, that is why it is to the right, right. So, you can see in the x axis, the blue is coming to the right of the red, right. So, men are generally taller than women. Similarly, if you look on the y axis, you can see that the women are in the lower part, men are in the higher. Men generally tend to be heavier, right. And more importantly, if you look along this, men tend to be heavier and taller than women, right. That is what it is saying. This is more taller, more heavier. This is less taller, less heavier, right. So, there is a correlation between them, right. So, that is what we are trying to capture, that is called the covariance, right, between the variable of height and the variable of weight, right. So, that is what height and weight has some relationship, and that is, if it is not 0, we say they are correlated, right. In the case of Gaussian, of course, that leads to independence and so on. So, therefore, we will now have to, and these are usually symmetric. If height is related to weight in some way, weight is also related to height. So, generally these covariance matrices will be symmetric. I mean, they have to be symmetric, and or at least if you are talking about real, if you are talking about complex quantities, then we will have something called the conjugation. So, it will be a Hermitian kind of a property that will come through. So, the height with itself, so that is the weight variance, the weight with itself, the variance, and the correlation, right. So, now we have how many parameters? If it is a bivariate, because there are two measurements, the mean itself will be two values, and the covariance with variance of itself, variance of the weight itself, and the only one half, because the other half is symmetric part. So, essentially you will find three variables coming for the covariance variance kind of thing, because sigma 2 and sigma 1 2 are related somewhat, and mu 1 and mu 2. So, you see that the parameter count increases when the number of parameters increase. So, if I have 3 measurements, let us say height, weight and chest size, then the mean will become mu1, mu2, mu3, the height, the weight and the chest size. Now, the covariance matrix, this will become 3 by 3 matrix, the variance of the heights itself, the variance of the weights itself and the variance of the chest size. So, they will be along the diagonal. The off diagonals now will have sigma 21 and sigma 31. Sigma 21 is how is weight related to height and sigma 31 is how is chest size related to height, right. So, there will be some correlation between them also, right. And again, because it is symmetric matrix, chest size versus height and height versus chest size, the relationship will be symmetric. Therefore, we need only the lower or the upper part of the matrix along the diagonal and upper or along the diagonal and lower, that information is necessary. So, the parameter counts keep going up, right. But maybe with more and more measurements, my confidence, my errors will reduce, because I am modeling the data better, I am modeling the class of males better, because now heights and weights are definitely going to give me more confidence in the measurement, because each one of them is giving me some idea about the male. So, if I get more and more measurements that strengthen my decision making will be better, and therefore, the errors will reduce. Okay. So, that is the basic idea of a bivariate. Okay. So, how do you compute the covariance? This is a mathematical idea, right, and if they are uncorrelated, we use it becomes a diagonal covariance. That means the relationship between height does not affect the weight, or the weight does not affect the height. Similarly, chest size does not affect the height, the chest size. So, the off diagonal elements which are capturing the relationship between them, they all go to 0. The variance of each one of those measurements will still remain. That is why it will become a diagonal measurement. Okay. So, again, this is what I am repeating it. So, heights and weights are correlated, and the correlation will show up as some kind of a relationship, right. So, there is y equals x, it is sort of towards, it is going in one y equals x kind of a direction, right. So, that is what we are trying to show here. Okay. So, now if I have heights and weights, now I can again repeat the problem that I talked about before, where we had a binary classification, is it a man or a woman. Now, I am having 2 measurements, both height and weight, and it should help me hopefully decide better if these are all giving me additional pieces of information that will make my decision making better, right. So, now I am having 2 dimensional features, both height and weight, and so I collect all the measurements of heights and weights, also know which gender it came from, men, and I built a bivariate Gaussian for the male model, right. Similarly, I measure all the heights and weights of females and build a bivariate Gaussian for females. Now, that is why this x axis and y axis are the heights and weights, and the curve is coming out. This is the curve that comes out. I could have histograms coming, like pillars coming out of the page, or I can fit a nice curve, right, which a closed equation, right, and this is the equation that we try to fit, or I can have pillar like histograms for 4 feet 5 inches and 56 kgs, how many people are there, 5 feet 1 inch 70 kgs, how many people are there. So, in the 2 dimension I can have pillars like our histogram before, or I could have a nice curve like this. Okay, something like this. Okay, so the bivariate, right. So, this is the equation, the closed form, mathematical way of describing it, and therefore, the unknowns now become the mu vector and the covariance matrix. So, given the data, I am going to estimate, but I know now it belongs to the male category. So, I again do a likelihood estimation, and it will turn out that the mu1 and mu2 will just be simply so I can show you, it will be a very simple idea, right. So, if I have measurements, right. So, if I have now measurements of height h1, w1, sorry, let me make it blue. So, if I have h1, w1 for the first male, so all the blues are males, h2, w2 and h500, w500. These are heights and weights of males. Then the mean is very simple. Mean will be mu will be the average height of male and the average height of weight of male will be nothing but 1 by 500 summation hi wi, which are coming from here. Okay. And same thing, the covariance is a little more complicated, that I showed it just now. This is the mu male. Similarly, if I have red ones, right? So now I have red measurements which are all coming from women, H1, W1, H2, W2, and let's say I measure for 500 women here also. So these are women measurements, female measurements, then measurements, then the mu of female, which is H female average and weight average, will just be 1 by 500. This red ones now, HIWI. Okay. So it's very simple. This is the maximum likelihood estimate for a bivariate Gaussian. So similarly, you can, I am not going to go into finding out, I am not going to go about explaining how we do it. It's described somewhere here. Okay. So similarly, we can do for covariance. Okay. Let's not worry about too much for it. So I have, by a maximum likelihood estimate, fitted the two curves for heights and weights for the male population, and similarly heights and weights PDF, the two-dimensional bivariate Gaussian for the women, right? Now I have to obviously make a decision, right? How am I going to make a decision? Again, we are going to use a principle of likelihood. So given a measurement, now somebody is in the other room, he says 6 feet 2 inches, 63 kgs. If he says that, now based on two measurements, I have both the height and weight measurement. Before last class we had only talked about heights, now we are talking about heights and weights. The person in the other room is saying, now I have to decide based on 6 feet 2 inches and 63 kgs whether that person I think is a male or a female, right? And the way I am going to do is the bivariate Gaussian from the male more likely to have generated, or is it the bivariate Gaussian from the female model that's more likely to have generated? So whichever is more likely, I'm going to say it's male, otherwise it's going to be female, right? So the same thing, and again errors are going to come in. We are going to make errors. Now it's in the bivariate space. What's the probability of the males being misclassified as females, or the target present misclassified as not present, right, and so on. So again there will be always errors, but with a better model, that is with the two measurements, maybe the error probability is going to get reduced. That is what we mean by a better model. Still there will be probability of miss and probability of false alarm, but both we can improve by basically getting more information, more measurements that actually help in the decision making. It's not no use if I say age probably is not going to help me decide as much about the gender, right? I say age 73. How do I know based on 73 whether it's a male or a female, right? That is not that informative, right? So when we talk about features, we want features that help us distinguish between the two classes, right? Some measurements may not be useful, so that is not a useful feature. Age might not help me decide on the gender so easily, right? So, but heights and weights can to some extent, right? So, this is as far as single Gaussian goes. Now, I am going to come to an important problem called a mixture of Gaussians, okay? So, first I talked about a single variable Gaussian, height for example. Then I talked about a bivariate or a two variable Gaussian where I had two measurements, height and weight, or three measurements, height, weight and chest size, right, and so on. And then we said the same way we can deal for a pattern classification problem, which is we decide which is more likely to have generated which distribution, and based on that we make a pattern classification problem.